One example of application of high-resolution electron microscopy in physics. Yutao, you have at about 1 hour and missing with 10 minutes left, I will let you know.
Okay.
Okay, if you go ahead. Thank you in advance again, and go ahead.
Okay, thank you. I think Professor Albino.
And also Bustamante is present now. They are present now.
Yes. Good morning, Professor Albino.
Morning.
Good morning, everybody. Buenos dias, buenas tardes, good afternoon. What more? How should I say in Chinese, Yutao?
早上好。
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 早上好。Okay, go
good
ahead.
Morning. Yes. Good morning, good afternoon, good evening to everybody. First of all, I would like to thank Professor Oliveira inviting me to give a seminar about our work. So my talk will be about superconductivity in nickel-bismuth systems. It's an example for the application of high-resolution electron microscopy in physics. So before my presentation, I would like to introduce my group, the research group. We have 7 professors: Dante Francestini, Fábio, Grauco, Juan Lucas Naches, Stefan Soriano, Professor Wallace Nunes, and I, with 7 researchers, staff. And then this is our old photo taken in 2019. It's quite old, out of our building. And we have different research lines, research interests. For example, nanomagnetism, carbon materials, superconductors, new energy materials, thin films, nanoparticles, plasma, and other nanomaterials. So we have 3 labs in our group. So we have the Nanomaterial Production Lab, RPN, and High Resolution Electron Microscopy Lab, we call it LAFMAT, and Material Characterization Lab, LCM. So we have different facilities installed. One example is the pulsed laser deposition. We call it a new pulsed laser deposition because we have a old pulsed laser deposition. We mount this machine in our laboratory, and we bought only pieces, and it was working very well. And we have, of course, we have several old facilities like plasma enhanced chemical vapor deposition. This 2, and one normal chemical vapor deposition. And then in our lab LAFMAT, we have 3 facilities. First is SEM, is a field emission SEM, GL 7100F, and we have a transmission electron microscope. Also, it's also a field emission microscope with high resolution. It's working very well. And very recently, we installed a focused ion beam from TESCAN. And then the inauguration will be on 27th of March, this month. So we will have a very nice meeting, workshop, and of course, very famous, we will have churrasco. And then in our characterization lab, we have a Raman spectrometer and a tribometer, and also a portable infrared spectrometer. This is more or less our facilities installed in our labs. And then I come to the topic of today. It's superconductivity in nickel-bismuth system. So for the people studying, doing research in superconductivity, it's well known that nickel It's a magnetic material. It's a ferromagnetic material, and it's non-superconducting. It's very well known. And the bismuth, at the beginning, it's also it's not superconducting. I mean, crystalline bismuth down to it's not superconducting down to 50 millikelvin. Only recently, a group from India, they showed that the very small single crystal of bismuth can be superconducting below 50 millikelvin. But if we deposit one layer of nickel and then another layer of bismuth by layers, even prepared at room temperature or at 100 Kelvin, the sample is superconducting. So where comes the superconductivity from this bilayer, nickel bismuth bilayer? So the TC is quite high comparing with the TC of a pure bismuth. So it's about 4 Kelvin. And then there are many interpretations. For example, it was concluded that maybe it's formation of the nickel bismuth 3 intermetallic compound. And the other said, oh, it's a nickel bismuth interface induced the superconductivity in bismuth layer. And then others said the bismuth here induced superconductivity in nickel layer. And then even someone said, oh, a very thin amorphous bismuth layer at the interface can be formed. So because it's well known, it's also well known that amorphous bismuth is a superconductor. And then recently in 2017, they said it was reported that magnetic fluctuation can induce superconductivity in this bilayer system. And at last, also, it was reported that bismuth at its interface can take the FCC structure of nickel, because nickel is FCC, bismuth is rhomohydrical, and then bismuth can take the FCC, and FCC bismuth is a superconductor. So it's a very complicated. There are many different interpretations. So our work, first of all, we prepared nickel bismuth bilayers at room temperature. So for sure, we know that at room temperature, it has to be a superconductor. And then we also prepared samples the bilayer at 4.2 Kelvin. Why we do this? Because at 4.2 Kelvin, the temperature is so low that there's no diffusion between the two layers. And then we performed very detailed microstructural study to see what happened at the interface, because the interface is very important. So first of all, I would like to show the transport measurement. We can see here is we fixed the thickness of bismuth, and by changing the thickness of nickel layers, we found they are superconductors. Even we deposit a very thin layer of bismuth, the nickel, it has already become a superconductor. The superconductor transition is around 4 Kelvin. But if we increase the nickel, the thickness of nickel, a two-step transition appeared. Of course, this is for us is quite new, because nobody reported the two-step transition. And then we studied the two-step transition in external magnetic field. We applied 0 Tesla and to 4 Tesla. And then we found out that the two-step transition, it behaves very differently in the external magnetic field. Of course, we also fixed the nickel layer here. And by changing the thickness of the bismuth layer, we also have different behavior. And then this is a first indication that there may be two different phases inside the bilayer. And then we did the microstructural study. This sample is our first sample I prepared with the FIB, the focused on beam, I was expecting at least an interface between nickel and bismuth. And from this figure, we can, this is, as I said, this is our first image of our sample. And I couldn't see any interface. There's no interface. And then we did the EDS scan, the line scan here. And then we can see that the nickel and the bismuth are mixed completely. There's no interface. So I was a little disappointed at that time because I wanted to see the interface, but there's no interface. And then I studied another sample with very high, at least higher thickness, a little bit thicker nickel, 40. That one is a nickel 2. And then if we study the nickel 40, the thing is 40 nanometers, there has to be a nickel layer. And then here, we showed a low magnification image, and the silicon oxide is our substrate. The black area here is our sample. The carbon film is deposited only just before the sample preparation with FIB, because I want to isolate our sample with the platinum deposited on the surface during sample preparation by FIB. So it's very clear to see where our sample is. Here it's very clear to separate with the platinum. And then from the high resolution image, we can see there are 3 layers. In fact, I deposited only 2 layers. First the bismuth and then nickel. But it appeared 3 layers. And the first layer here is the last layer I deposited nickel. So the first one is I was thinking about nickel. Okay. And then we did the conversion beam diffraction. So we did the diffraction only one point here with the diameter of more or less like 2 nanometers. So the first one here is very easy to index. It's FCC nickel. There's no difficulty to index this pattern, diffraction pattern. And the 2, here we index it as nickel bismuth 3. And now when we come to layer 3, I was thinking, of course, it should be bismuth, pure bismuth, because the first we deposit this layer pure nickel, pure bismuth, and then pure nickel. Okay, they reacted and formed the second layer, and then the third layer should be pure bismuth. And then I tried at least 1 or 2 weeks trying to index this pattern, the diffraction pattern. I couldn't. It's not bismuth, pure bismuth. Then I give up the pure bismuth, and then I started to look for other compounds between compounds of bismuth and nickel. We saw there is another compound, nickel bismuth, nickel 1 bismuth 1, and then it was indexed here at nickel 1 bismuth 1. So it is another intermetallic compound of nickel bismuth. And then to confirm this, I have to show the concentration. And then we did the mapping, EDS mapping of the cross section. So we can see here the nickel, and then at the border here, the concentration of nickel increased. And then I did a line scan here, a line scan to show the concentration of the nickel, the yellow curve. And then we can see at the end, the nickel, the concentration of the nickel increased. And of course here, this layer is the bismuth. It has more bismuth. This side is silicon, and this side is carbon. When I did the line scan, of course, the result shows clearly that the nickel increased as the interface of silicon and bismuth. But other people can argue that maybe the line is passing one particle of nickel during sample preparation, Okay, then I also did the average. It's not a line scan anymore. It's an average of this area, all the spectra. And we can see here, this figure. And also at the end, nickel, the concentration of nickel increased. It shows clearly that here at the end, nickel, the sum has more nickel than in the middle here. So then we come to the nickel bismuth phase diagram. We can see here is a 100% of nickel, and this one bismuth, and this side is 100% of nickel. And in between, there are two intermetallic compounds. Bismuth 3 nickel, because it's close to bismuth, it has more bismuth 3, 1 nickel. And when it goes to close nickel, it has 1 nickel and 1 bismuth. The compound is bismuth 1, nickel 1. So the order is bismuth, bismuth 3 nickel, bismuth nickel, nickel. So it's here. The phase distribution in literature is nickel, nickel, bismuth, nickel, bismuth 3, and the bismuth. But in our sample, in our work, it's nickel and the nickel bismuth 3 and the nickel bismuth with here with less nickel than here. And then there is our substrate silicon dioxide. So it's very, very different from the literature. So with this result, we can confirm that in our sample, so it formed nickel bismuth 3 and nickel bismuth with TC around 4 Kelvin. But all the others, I don't know. We can confirm only this interpretation, but we cannot rule out all the others. So still, the argument still is going on. So we did the second part of our experiment. We deposited the sample at 4.2 Kelvin. Why we deposited at the 4.2 Kelvin? Because at that low temperature, so there's no interdiffusion between nickel and the bismuth. So it will be very difficult for the nickel and the bismuth to react. Now, here's the first curve. Is we cool down the substrate to 4.2 Kelvin. And then we did the low temperature deposition. And then we measure the transport in situ. This has been done in situ. So here we can see at more or less like 5 Kelvin, there is a transition from zero resistance to more or less 500 ohm. And then with increasing the temperature, then we see another transition until 60 Kelvin. The first transition is the superconducting transition of amorphous bismuth. As I said at the beginning, amorphous bismuth is a superconductor with TC around 6 Kelvin. So the first transition here is the superconducting transition. And the second one is the crystallization of amorphous bismuth to crystalline bismuth. But why the crystallization increases the resistivity? This is because, as we know, bismuth is a semi-metal material. It's a semi-metal. So the density of states is very low. There are very few free electrons inside the bismuth. But the amorphous bismuth is a metallic. It's a metal. So that's why amorphous bismuth has lower resistivity than crystalline bismuth. And then this one, after the bismuth is crystallized, we heated the sample to 300 Kelvin, and then we come back. This is the curve that come after the annealing at 300 Kelvin. So this one, we can see that for sure. Now we have a layer, a very nice layer of crystalline bismuth. So it's not amorphous, it's crystalline. And then we cool down the sample to 4 Kelvin again, we deposited another nickel layer. So this one, the red one, this is after deposition of a nickel layer. This one is also the measurement that was done in situ here. And when we do the measurement in situ, we couldn't find any superconducting transition. So, but for sure, we have the interface of nickel and the bismuth, this one. And then after the in situ measurement, we cool down the sample again to 4.2 Kelvin, because after annealing, the density of defects decreased and the resistance decreased, but still, there's no superconductivity here. It means the interface of the nickel bismuth cannot induce superconductivity. Since we installed the machine there, we installed the substrate, we want to prove it. So with this sample, we cooled down to 4.2 Kelvin, we deposited another bismuth layer. Again, we can see the transition, the superconducting transition of the third bismuth layer. And then the crystallization, after that one, we come back, no superconductivity. Of course, we have to show the structure, the microstructure of this sample. We see bismuth 35 nanometers, nickel 5 nanometers, and bismuth 35 nanometers. Here is a low magnification image. You can see bismuth, nickel, bismuth, silicon dioxide, carbon. So you see we controlled the deposition very well, and you can see the two layers of bismuth is exactly the same. And then in the middle, there is a very thin nickel layer. So we did the EDS analysis. We can see it is the bismuth in the middle is nickel. And then we, with the high resolution image here, we can index this layer is pure bismuth very easily. It's really pure bismuth. There's no nickel here. And then with this result, we ruled out these interpretations. The superconductivity has nothing to do with the interface. So it's the intermetallic compound nickel bismuth 3 and nickel bismuth. But we cannot rule out the last one because bismuth, if bismuth can take the FC structure of nickel or not, because we deposit the nickel at 4.2 Kelvin, the nickel is also amorphous. It's not FCC, so it's amorphous. So we cannot rule out this interpretation. So we performed the third part of the experiment. So first of all, we see we did the low temperature deposition of bismuth here. No, first we deposited of nickel first at the 300 Kelvin. So we showed that the nickel is no superconducting transition. And then we cooled down the sample to 4.2 Kelvin and then deposited bismuth. And now we have a crystalline nickel. Above is amorphous bismuth. And then we did the measurement in situ. We can see this acid transition due to the amorphous bismuth. And then after the crystallization of bismuth, we come back. Now here the red curve shows the crystalline nickel and the crystalline bismuth. There's no superconducting transition. So with this experiment, of course, we can see the structure. Here's our substrate, and this layer here is nickel, and this side is bismuth, and the outside is carbon. And then we can see the high resolution image, and then we can see now the nickel here is crystalline nickel, and this side is crystalline bismuth. There's an interface and no superconductivity. So with this, we also did the EDS analysis. We confirmed that here, the nickel here, and the bismuth, there's no increase of concentration of nickel again. Here we can show clearly this is nickel, and here is the bismuth. So with this result, we also ruled out the last one. So in fact, the bismuth is not taking the FCC structure of the nickel. In fact, they formed different compounds, nickel bismuth 3 or nickel bismuth, depends on the energy of the atoms arriving at the substrate. Of course, this is our first experiment to show that the origin of the superconductivity is from the reaction of nickel and bismuth. Of course, there's also many other problems. For example, controversy of deposition order. Somebody said here, it was reported that the superconductivity occurs only in samples with nickel deposited first and then bismuth layer. And the others said no, they don't depend on the deposition order. And we also want to see what happened due to this too, due to the different deposition order. So our first position, when we were trying to do the different samples with different deposition order, the first one is if we deposit bismuth first and then nickel, for example, bismuth 40 nanometers, nickel 4 nanometers, and then the sample is mirror-like. The surface is like a mirror. It's like the normal metallic thin films. But if we deposit first nickel 4 nanometers and then bismuth 40 nanometers, it's like a frosted-like surface. It's not shining anymore. So it's very strange for us. Why? It's not shining like the first sample. And then, of course, if we also prepared pure bismuth and pure nickel, all of them, they are mirror-like surface. So we first of all, we took the sample to the SEM. We have the machine installed to have a look. And then first of all, this one is pure bismuth. We can see the bismuth formed a layer, a continuous layer. Even there's several small crystals on the surface. We even can see the green boundaries here. And the nickel is completely flat. And I show here a defect of the film only because I just want to show the focus of the image. Otherwise, we don't know if we focused on the surface or not, because it's very, very flat, very clean, very flat. So in fact, it was difficult to find this defect to show the surface. And then if we really see the two samples, they are very different. The morphology is very different. So here, the sample first we deposited bismuth and then nickel. It's like the original bismuth pure layer. If we can see, compare this one and with this one, they are almost the same. You see, only with very small bismuth crystals on the surface, and the whole surface is almost flat. This one is almost the same with the pure bismuth layer. However, if we deposit first the nickel and then bismuth, the morphology is very, very different. There are many small particles and the nanoparticles on the surface with the diameter the diameter less than 200 nanometers here, the scale. And if we see the cross section, we can see we couldn't even find a nice continuous bismuth or bismuth 3 layer. They formed all the sample almost formed the islands here, the small islands. So what's the difference of the not the chemical composition? They should be the same because we deposited the thickness, they are exactly the same. But the morphology is very different. We have to start with TM. And we started here. The TM, with the TM image, we can see the bismuth 40 and nickel 4. They are full of stress inside. This is a contrast of the neutral string in the sample. And also the particles, the black particles, we show that the particles a little higher, the crystal line. We studied the high resolution study, it's nickel bismuth 3. And of course, we can see the continuous layer here. It's also nickel bismuth 3. It's not bismuth pure bismuth. It's not pure nickel. It's nickel bismuth 3. All of them nickel bismuth 3. And of course, we can see the dislocations here, and a lot of string. But if we do the EDS analysis, we confirm the homogeneity of the nickel and the particles, the black particles is nickel bismuth 3. And for another sample, the first nickel and then bismuth, we can see there are many nanoparticles on the surface. And then we did the selected area diffraction, and we can see there is very small pure bismuth left, and most of them are nickel bismuth 3. So by this, we can conclude that they reacted, even it does not depend on the deposition order. The nickel and the bismuth reacted with each other and formed nickel bismuth 3. This sample has been done by sputtering. The TM, the EDS results confirmed observation. You see the bismuth here. It's accumulated. And it's very interesting for us that we started to analyze the physical properties of all the materials, because we tried to understand why it occurred like this. It's very interesting that you see for the reaction, nickel plus 3 bismuth formed nickel bismuth 3. So 1 more of nickel plus 3 more of bismuth we will obtain 1 more of nickel bismuth 3. It's very interesting that the volume of the production nickel bismuth 3 is even less than pure bismuth here. So at the beginning, I thought, no, it couldn't be, because just imagine we have bismuth and we put nickel, they react. Of course, then the reaction the volume may be smaller than the summary of nickel and bismuth, but should be higher than bismuth. No, it's smaller. The volume is smaller even than the pure bismuth. That's why it's so easy for nickel and bismuth to react. It's very easy, because even we just imagine we put 1 atom on the surface of bismuth, and then when they react, the volume contracts, the volume becomes smaller. So when the nickel atoms go into the bismuth, it induces collapse of the bismuth. And then we proposed different nucleation group process. For example, when nickel comes to bismuth, like 1 atom of nickel needs 3 bismuth atoms to react to create nickel bismuth 3. So, and when 1 nickel reach there, it can form nickel bismuth 3 and nucleation, and then when the more nickel comes, and then the nuclei just grow and form larger rings. And also each nickel atom reach there, they can induce the growth, the nucleation. On the other hand, if we deposit bismuth to nickel layer, so the first bismuth reach there, it cannot react, because 1 nickel needs 3 bismuth atoms. So the 3 bismuth atoms must wait for the 3 bismuth atoms and then form a nickel bismuth 3, and then reach another bismuth atom, and then the bismuth atom has a very high activity on the surface. It's very easy for them to move, and then it's much easier for them to just migrate on the surface, and then let the nickel-3 growth, not nucleation. So the nucleation is much more difficult than the growth of nickel-3. For this reason, at the end, they formed the pillar-like structures with a very thin layer of nickel-3 left on the surface. So also we published the result in 2021. And of course, we studied the superconducting transition of two samples. It depends on they show different behavior only because of the different morphology. And the last one example is the shape, resonance, and the TC oscillations in nickel bismuth systems. So the idea is very easy. So if we prepare a thin film of the superconductor, and then the wave function depends on the thickness, it can form how to say it, stationary waves. So it depends on the thickness. So if we tune the thickness, so we may have higher TC, or the TC oscillation may occur. So but to obtain this one, first of all, the thickness should be comparable with the coherent length. So the thickness should be much smaller. It cannot be quite thick. Quite thick will observe anything, will not observe anything. And the second one, the mean free path should be higher than the thickness, because it should, the co-pairs shouldn't have scattering just between the two layers, between the two boundaries. This one is very, very difficult. Usually for the superconductors, so the mean free path is quite short. So comparing with the thickness of the samples. So for this reason, it's really difficult to observe the TC oscillations in superconductors. But bismuth, it has a very long penetration depth. So in this reason, we tried this work. I discussed many times. So it's a collaboration with Professor Mauro Doria of Federal University of Rio de Janeiro. So we discussed many times, and we calculated, and then we discussed a lot about probably about the mean free path of the bismuth. And then at the end, we tried to do some experiments and together with calculation. And then so we planned several samples with different thickness, and here also several samples with different thickness. Try to see the TC, and then here is the measurement, the transport measurement of the nickel bismuth with the TC like this. Of course, this one, the first one, because it's very thin. So when the sample is very thin, it cannot form a complete nickel bismuth layer. So the TC is very low. Even there's no complete transition. But the other samples, it seems like oscillation. And then another a series of samples here. We show this one is also very. You see here, it's not a complete superconducting transition. For this reason, TC is quite low, and it has like I cannot conclude this oscillation. But the first one here, much better. And then this is calculated by Professor Mauro Doria. I couldn't understand too much of this one. He calculated, and it seems that this with parameters here, it seems like the TC is oscillating. So this part, I was responsible for the experiment part, and the Professor Mauro Doria is responsible did all the calculations, and so we published the results last year. superconductor science and technology. So I think this is my presentation. I give a summary. High resolution electron microscopy is a powerful tool for research in physics. Of course, I also open for collaborations. If you really need something, for example, the microscope or pulsed laser deposition or Raman spectroscopy, just we can have a talk or just come here to do the experiment. I can arrange the machine time. And then I would like to thank my colleagues, the lab nano at CBPF, because we prepared our FIB samples at the CBPF, the CMBK, PAPED, CAPES, NP Petrobras supported and we bought the SEM, TM, and the Raman spectroscopy with the support of Petrobras, with the financial support. And thank you for attention. I would like to finish my talk with a plaque in my lab. Coisas boas acontecem aqui. Vim para nosso laboratório, para dar seminário, para conversar, para fazer pesquisa junto. So we can do much more better things. Thank you very much. Good morning, good afternoon, good evening.
Thank you very much, Xing. Thank you very much again. Very nice talk, very interesting work. And now we'll ask some questions for you. The first one that I will call for ask you is Professor Albino. Albino is here. Albino? Okay.
I am here, of course.
Okay, Professor.
I cannot miss this talk. Very important people. Okay.
Okay, go ahead.
Yutao.
Yes.
Parabéns pela excelente palestra. Você tem muito resultado. Eu acho que a gente precisa conversar mais.
Sim, sim.
Porque nós temos os resultados de 2015. Não é de níquel bismuto, é o velho nióbio e chumbo. Os dois velhos. E a gente tem coisas parecidas. Eu vou mandar para você o artigo.
Sim.
E aí a gente conversa. Tá certo?
Tá certo.
Por favor, mostre lá aquele seu gráfico que tem a transição em dois steps.
Ah, sim. 2 steps no aqui. Aqui.
Nós temos coisas parecidas.
Tem parecidas?
Tem sistema, muito parecida. E a gente tem lá uma interpretação com uma teoria que era conhecida na época, que talvez possa se aplicar aí. Então, se você mandar os resultados, eu vou mandar o meu artigo e a gente vai discutindo.
Sim, sim. Porque a gente explicou aqui que eu descobri 2 fases. Porque níquel bismuth, níquel bismuth 3, os dois são supercondutores. E para as amostras, eu não sei, eu tenho que ver, eu acho melhor, faço um estudo de microscopia com mais cuidado para ver o que aconteceu.
Sim, porque senão nossos amigos lá do hemisfério superior vão falar sempre que é bad quality sample.
Ah, sim, ele fala bad quality, mas aqui eu mostrei que não é bad quality, né? Realmente 2 coisas diferentes.
The last time they said this to me, I answer like that. Look, if this is bad quality sample, imagine the good one. Try to do the good one.
Yeah.
We are doing good sample, sir. So, these guys are terrible. But eu acho que a gente tem coisas semelhantes.
Sim.
Nós estamos tentando produzir de novo outras coisas.
Sim.
E aí tu me envia esse artigo, eu estou enviando já para o seu e-mail a cópia do nosso.
Eu já falei.
A gente se vê breve, viu? Eu estou lhe devendo um documento, mas eu mando segunda-feira, que é feriado aqui.
Tá, então manda o seu documento para mim, para eu resolver a passagem.
Sim, também.
Sim,
Eita,
reservar
esqueci
passagem.
Tá bom.
Eu já falei para o professor Isaías Oliveira, e aí a sua visita vai ser em abril, tá? Eu já falei para eles.
Isaías disse que eu tenho que me hospedar lá em Medina. Bom, mas a gente conversa isso.
Tá.
Um abraço, muito obrigado. Obrigado, Isaías.
Obrigado,
Thank you very much. Bye.
Okay. The next the question is Professor Stewart. Stewart, is your time.
Okay.
Yes.
Okay. Thank you, Professor Xing. Very, very interesting work. I think I understood some of it. This is a question maybe about future work. Have you considered maybe growing nickel on bismuth nanowires? So you can make in situ bismuth nanowires very easily. I can send you the reference if you don't know. So, you know, reducing the dimensions down to a nanowire might be a good forward development for the work. Do you have any comments on that?
Yes. To be honest, when I was trying to do the thin films, one sample I got completely, all of them, they are nanowires. So I didn't show it here because I didn't publish it yet. So I'm thinking that they must be nickel bismuth 3 nanowires. It's not pure bismuth because at the end we deposit a nickel layer. But I'm not so sure. I didn't do the study, the transport study, because at that time we didn't have I5E installed. I cannot make the nano contacts. Yeah. So my working plan is to make the nano contacts, to do the transport of the nanowires. Of course, I have to repeat. I have to compare the pure bismuth nanowire with deposition of nickel. This is very important. Of course, I still, to be honest, I got the sample. I didn't know why.
Sometimes the way, yes.
I didn't know why. I'm trying to repeat the result. But if you have, I don't know, if you can prepare nanowires there, and we can do the collaboration.
I can't myself, but I collaborated with the university in Korea, Yonsei University in Korea, and they were able to make bismuth nanowires. Very, very nice, high purity, almost ballistic. Almost.
Okay, this is very good. We can, if you can send me some
send you the
wires.
reference. Yeah.
Yes, and then I can deposit nickel on top, and then try to study the transport before and after the deposition. It will be very interesting.
Sounds. Thank you. Yeah. Thank you for your talk again. Very interesting. Thank you.
Thank you very much.
Thank you, Stuart. Thank you, Xing. Again, José Fermier, are you here?
Yes, I'm here. Obrigado, Isaías. Albino. Bom dia para todos. Thank you, Mr. Xing, for your nice talk. Muito obrigado pela sua presença cá conosco.
De nada.
Now, I have no questions. Não tenho perguntas por enquanto. Muito obrigado.
Okay, obrigado, José Fermier. Thank you very much, José Fermier. Thank you, Xing, again. Now, Sergio Conejeros, are you here?
Yeah, I'm here. Hi. Good morning here from Chile. So, very interesting talk, Professor Xing. I really enjoyed it. And I would like to know, because you just showed or presented just experimental results. So I would like to know if you collaborate with people who perform computer simulations, like for instance DFT calculations or something similar.
At this moment, I'm collaborating with Professor Mauro Doria, one theoretical, but I theoretical physicist. Of course, I would like, of course, I would like to collaborate with my other physicists with theoretical calculations. If you have the interest, we can collaborate.
Okay, thank you.
Sure, for sure. This is for sure. We can discuss the future work together. For example, my last work with the Professor Mauludolia, we started the discussion many times. We started discussion in, I think, 2 or 3 years ago. We started the discussion. I showed him my results, and they showed me the idea, and we discussed if this is possible or not. And then at last, it came out a very nice article. I think this is also very interesting and important for all of us. The collaborations is very, very important, because for me, at least, only the experimental part, it's difficult to do everything alone. Impossible. This is impossible. So we have to collaborate. Yes.
Okay, thank you very much for your talk again, Professor Xing.
Sergio, they are using Bogoliubov-Digenes model to try and understand these transitions.
Okay.
Okay. Thank you, Sergio. Thank you, Yutao, again. Ximena, are you here? Ximena, do you have a question? Ximena? Okay. Any other person have a question to Professor Xing?
Profe, ¿cómo está? No tenemos preguntas. Qué pena con usted, tenían problemas con el micrófono. No tenemos preguntas para el profesor, solo agradecimientos. Gracias.
Okay, thank you very much. Okay, Yondres, go ahead. Your microphone, please.
Yeah, thank you, Professor Xing, by your presentation. Very interesting. My question is very, very simple. I want to know about the thickness of the sample that you use to obtain superconductivity. Exists any relation between the thickness of the samples and the critical temperature that you obtain superconductivity for the sample of nickels and bismuth?
Yes, here we can see the I didn't show the result. We have the thickness here. We have even this sample, we have the thickness of bismuth 38 nanometers fixed. We are changing the thickness of the nickel, and then we have different TC. Of course, the TC is and a different transition. And here we have fixed the nickel 2 nanometers, and then we are changing the thickness of the bismuth. We have different TC. So it's clear with my last work here with the Mauludolia, we are only studying the TC as a function of thickness here. For example, this sample we keep the ratio of nickel and bismuth fixed to 12, 4, 24, 6, 26, 8, 48. We can see the TC variation. And for this sample, we got nickel fixed, but we are changing the thickness of the bismuth. You see here, nickel 3, we're changing the bismuth because we are doing this sample only because here, I didn't show it very clearly. We assume here that the superconductivity is from the nickel 3 layer, but it can penetrate to the pure bismuth layer. And then there's an energy barrier for the Cooper pairs to pass, but still, after the calculation, it shows even at the side of the pure bismuth, there's a very weak Cooper pairs, the signal of Cooper pairs, the will function. So that's why we did many samples with different thickness, fixed, or with the ratio fixed, or with the nickel fixed, to see the variation of the TC.
All right. Thank you, Professor. Thank you.
You're welcome.
Okay. More any questions? Okay, if you don't have more questions, if possible, open your webcam to thank Professor Yutao again. Let's open our cam. Oh, my camera is open.
Isaías, tem alguém com a mão levantada aí.
Okay, sorry. Who is? Okay, Andres.
Oi.
Andres.
No, sorry.
Okay, no problem. Okay, let's thank again Professor Yutao.
Thank you.
Thank you very much, Professor Yutao Xing. Thank you again.
Isaías, o Andres tem pergunta.
E aí, a gente tem que o Albino e Isaías, a gente tem que se encontrar em abril, né? Aqui no Rio.
Sim. Vamos nos encontrar.
Olha, eu estou dizendo que o Andres está querendo perguntar.
No, Professor. My question was made.
Okay, sorry. Okay, Yutao.
Okay.
I'm looking forward to meeting you in Rio.
Yes, of course. In Rio, in abril.
Em abril.
E bom churrasco.
Churrasco em Medina.
Okay. For sure. We will have barbecue. Okay.
Okay, barbecue. Okay. Good.
Everybody.
Have a nice weekend.
Have a nice weekend.
Congratulations again for your help.
Ciao.
Bye.
Bye.
See you next week.
James, you can stop the record.
Hasta luego a todos.